Mount Rainier is a volcano that shouldn't exist. But if it doesn't follow the rules, why is it still standing tall today? And how might that affect its future eruptions? If you live in the Pacific Northwest like I do, you probably know all about Mount St. Helens and Mount Hood, two famous volcanoes in Washington state. But Mount Rainier looms even larger over the landscape, standing at over 14,000 feet or 4,362 meters high. That makes it the tallest of the four major volcanoes in the Cascade Volcanic Arc and the most massive active volcano in the contiguous United States. It's so big that if it erupted tomorrow, it would be one of the top 10 largest eruptions in the history of the world. Now, when I say it's the most massive, I don't mean it has the biggest base or is the widest at the top. I mean it's the most voluminous. In other words, it contains the most rock. It has built up more than 25,000 cubic kilometers of material during its existence, which is nearly 8 times more than St. Helens. Its summit alone is made up of over 70 cubic kilometers of magma. But here's the weird thing. Geologists say that Mount Rainier shouldn't have built up so much magma in its chamber over time. So what gives? Well, let me start by explaining how we determine whether a volcano will erupt or not. It turns out that there are some key factors that must come together for an eruption to take place. First, there needs to be enough magma present in the chamber below the volcano. Second, that magma must be hot enough to melt through the rock above it. Third, the pressure in the magma chamber must exceed the weight of the overlying rock column. Fourth, pathways or vents must exist for gases and magma to escape through. And finally, the magma must be less dense than the surrounding solid rock. If all these criteria are met, then an eruption is likely to occur. For example, Mount St. Helens had built up sufficient magma to meet the first criterion. The magma was hot enough to melt through the rock above it, meeting the second criterion. Pressure from the magma exceeded the weight of the rock column, meeting the third. There were vents that allowed gases and magma to escape, meeting the fourth. And the magma was less dense than the surrounding rock, meeting the fifth, so it's no surprise that it eventually erupted. On the other hand, Mount Hood doesn't currently have enough magma in its chamber to meet the first criterion, so it's unlikely to erupt anytime soon. That's why geologists say that Mount Rainier is breaking all the rules, because it meets all the criteria I mentioned earlier, except for having enough magma. Yet it still erupts periodically, and scientists aren't sure why. One theory is that Mount Rainier has found a way to make up for its magma deficiency by tapping into the heat from the Earth's core. You see, the Earth's core is extremely hot, but that heat doesn't just stay there. It radiates outwards towards the surface. In fact, the average heat flow from the core is about 20 times greater than the amount of heat we use worldwide every year. Now, the good news is that this heat doesn't normally affect us because it spreads out over millions of years. But sometimes the heat can be focused in one area, causing what's called a heat flow anomaly. These anomalies can increase the temperature of rocks near the Earth's core by several hundred degrees, enough to melt rock and form magma. In the case of Mount Rainier, this heat may be coming from a process called the stagnant lid model. In this model, a slab of cooler oceanic crust gets pushed under the continental crust, but instead of sinking all the way down, it gets stuck and forms a sort of lid on top of the Earth's core. As the new oceanic crust continues to push against the lid, the temperature beneath the lid rises dramatically, creating a magma chamber. Now, if this is happening beneath Mount Rainier, then that could explain why it has so much magma despite being further away from the subduction zone than other volcanoes in the arc. Basically, Mount Rainier is cheating by stealing heat from the Earth's core instead of relying on the subduction process. But here's the thing. We can't actually see what's going on beneath the Earth's surface to confirm this theory. Plus, even if we did, we wouldn't be able to tell if Mount Rainier is getting enough heat to make up for its magma deficiency. After all, we'd be discovering this heat after it's already melted the rock. So how do we know that Mount Rainier isn't following the rules? Well, we can infer that something unusual is happening by looking at the chemical composition of the magma. You see, when rock melts, different minerals melt at different temperatures. Let's imagine a mineral melting curve with temperature on the vertical axis and mineral melting point on the horizontal axis. The melting curve shows us the temperature at which a particular mineral will melt. For example, olivine starts melting at around 1000 degrees Celsius, pyroxene at around 1200 degrees, and quartz at around 1700. Now, these melting points are just averages. In reality, many factors can affect the actual temperature at which a mineral melts. But for our purposes, they're good enough to illustrate a key concept. As the temperature increases, the minerals become more and more incompatible with each other. In other words, they can't coexist in a magma chamber. If they do, the lower melting minerals will crystallize out while the higher melting ones remain liquid. That's why we find different minerals in different types of rocks. For example, gabbro is rich in olivine because it cooled quickly and didn't have time for the more complex minerals to form. Basalt, on the other hand, can contain pyroxene and other minerals because it cooled more slowly. And granite contains quartz because it cooled very slowly. Now here's where things get interesting. The Cascades are supposed to be rich in a mineral called biotite because their magma chambers are hotter than the average. But Mount Rainier's magma chambers are even hotter than that, so we should find only the most resistant minerals in its magma, and that's exactly what we find. Mount Rainier's magma is rich in quartz and alumina, which means that its magma chamber must be hotter than average. But that raises another question. Where is all the silica going? Silica is what makes granite, and granite is known for being highly viscous. So where are the giant bubbles of viscous magma we should be seeing in Mount Rainier? Well, it turns out that Mount Rainier's magma is actually quite fluid, which means it can travel long distances before solidifying. In fact, one of the main reasons why Mount Rainier is so tall is that its magma is so runny. Most volcanoes erupt with a mix of magma and gas that forms a cloud called a lava plume. The height of the plume depends on the viscosity of the magma. The more viscous the magma, the shorter the plume. For example, Mount St. Helens erupted with such force that its plume reached 33 kilometers into the atmosphere. But Mount Rainier's most explosive eruption only reached 30 kilometers. Why? Because Mount Rainier's magma was too runny to form a tall plume. Instead, it flowed outwards, building up the volcano's summit. Now this is great news for Mount Rainier because it means that it can continue to grow taller without triggering a major eruption. But it's bad news for the people living at its base because it also means that its lava flows are more dangerous. In fact, Mount Rainier is considered to be one of the most dangerous volcanoes in the United States because of the large number of people who live within its path. More than 200,000 people live within 100 kilometers of Mount Rainier, including the cities of Tacoma and Seattle, home to over 4 million people. A major eruption would cause widespread devastation and loss of life. That's why the United States Geological Survey monitors Mount Rainier closely and has developed a comprehensive plan to respond to any future eruptions. Now, all this talk about Mount Rainier has got me thinking, what if there are other volcanoes around the world that are cheating the system in the same way? Is it possible that some volcanoes have found a way to tap into the Earth's core and steal its heat? If so, then maybe they don't follow the rules either. Volcanoes are truly fascinating natural wonders, and I hope you enjoyed learning more about them today. Thank you for watching, and I'll see you next time.